now it's gonna go to the cloud. So hopefully if you can hear me, it's 8:45, it's in the morning of Tuesday, July 2nd. We have July 3rd tomorrow. There's a holiday and on Thursday, and then we have Friday when we come back for another lecture. That's the week number 3. So what I see in the chat is Ahmad, A. I see Chris Combs and I see Scott W. And in here in this room, we have John and I. So this is us right now. And as I said before, if I have nobody in the room, nobody online, I will still go record and set this up. I want to make sure that people can hear me. And so here's Alisa coming. We had a storm last week. On account of that, it was kind of difficult to set up week 2. I mean, I can contribute to that. Week 2 meetings. So now I think the plan is to combine week 2 and week 3. Although some people have met with me for week 2 and they will meet on week 3. So that was the best situation. It's just that it's okay if we combine week 2 and week 3 as long as we set up a time. And so that's what we are working on. I'm going to soon go to the website and then show you the updates, whatever. And before we do that, I want to make sure that you can hear me. And as I do before, I am kind of stalling for time, see if anybody else shows up and so on. Elmar just came up. So I'm going to ask a question and I want you to write down the answer in the chat. If you know the answer, if you don't know the answer, say, I don't know. This will be a confirmation that you can hear me. This is a simple joke. So what do you call an alligator that wears a vest? Is that a joke? I guess so. Everybody knows this. There's Carla coming in. So what do you call an alligator that wears a vest? That is correct, Alisa. So people can hear me. It's called investigator. This is a highlights joke. So for very young kids. I have better questions. But some of the best questions that I have are rhetorical questions. For example, let me ask John. It's a rhetorical question, so I don't know what your reaction is going to be. So what if soy milk is actually regular milk introducing itself in Spanish? That's a tough question. I mean, can you imagine the deception? Exactly. I agree completely with that joke. So we are ready to get started. I guess I have 7 people online. Let me write down. See, but that's also good. I mean, getting a ha is also proof that you have in fact heard me. So I'm gonna write down this one, and we are ready to get started. I'm gonna close the meeting chat, and I'm gonna close the participants, and I'm going to minimize this on the top, and I'm going to close the clock. If anybody needs anything, go ahead and write in the chat. I might be 1 or 2 minutes late noticing that, but it pops up and it doesn't make you forget. And then if you really want to stop me, just go ahead and talk. You will come through, I think. For example, let's verify. Alisa, can you tell me if you can speak? What's the time that you have an appointment today?
6.
That is correct, 6 p.m. So I heard you, and we just confirmed that things are working well. If anybody in the Zoom would like to speak up, we will hear you immediately. So
Good morning.
Hello, how are you?
Just fine. How are you?
Okay, good to hear you. So I'm going to click on participants. We have 7 people, and we're ready to get started. So this is a good test that if somebody says something without being properly, we immediately connect. So that's wonderful. So anybody who has anything could just say, and then we get the answer out. Maybe I would like to come up with a stop sharing, and I'm going to bring the video up. So my video, I don't know where my video is. This is me. Okay, I'm waving a book, and the book is I will show you the book in a second on Amazon. It's a very slim book. It has basically 63 pages. It's written by an undergraduate. I thought that they had Brown, but sometimes I thought Brown, but it's Brown University. So that's all I can do with respect to, because I don't know where the camera is. Oh, it's over there. I'm going to go back to sharing again. So you look at the website now for the course. I have updated this just minimally. I'd say yesterday was one, and here's the lecture of yesterday. And that's the video with whatever we did. Actually, let me just quickly tell you that this video is a little longer than we normally have on account 136. We capture some 15 minutes of discussion. And in the process of doing this, guess what? I took
Told me that
us to edX, to a course that exists on edX that is taught by Diana Franklin at the University of Chicago. And she was one of the first people who actually made a course out of Terry Rudolph's book. The example that you see over here is the exact example for tue0702 in the book by Terry Rudolph. And her problem here was, watch out, at some point you're going to give up on this method because it explodes. And sure enough, it explodes, okay? The method that we are learning in this class, the misty state formalism, it's very much like the slow motion replay that they use, let's say, in basketball to decide what happened, who did the ball touch last before it went out and stuff like that. Or how exactly was the foul and was responsible for it, yes.
Is this the reason that they say when you simulate quantum computing, then you need exponential memory, right?
Exactly. So nobody says you should watch a whole game in slow motion because that is just ridiculous. However, without slow motion, we will be really in trouble in some cases. And our goal is to watch in slow motion in the beginning, the foundations, and then graduate to the regular motion math. But I have the booklet that I told you about. It's right here under the link. And now I'm going to go to Amazon and type his name and show you the actual booklet. And I want to clarify that the booklet is expensive, 35 bucks for 60 pages when the actual paper is probably 30, because he does like 2 extra space between lines. I think you should take the PDF. So I'm going to go and say his name is this. And then this is the booklet that he wrote. So 35 bucks. It's a bite-sized introduction. It's very short, but believe me, it's actually quite accurate and useful. Therefore, I totally encourage you to read the booklet, not necessarily right now or with any kind of sense of urgency, but if you ever feel like I really can't get a hold of the math of it, then you can open the booklet, and that's how it works. So why am I introducing this now? First of all, because I found it 2 days ago, even though I looked for it a year ago, and because we are doing tue0702 algorithm. This book, he's an undergraduate, and the book is very crystal clear, and he explains who's the advisor and why he wrote this paper. That was just a semester project. And then he published it, self-publishing, I suppose. And I totally appreciate the book. But if you want to search in this book for the name Helber, he says this is a talk that was very helpful to me in writing this. And the truth is that a lot of the book is actually just following Helber. I have no idea. I have no problem with that. This is an undergraduate who understood and now says, let me just teach you what I was taught. And that's totally fine. So now I would ask anybody, where did I put the Helber links? There's always a problem because my websites don't have an index, because I say you should provide an index with your notes, and you don't have the index, you don't know where it is. And I also forget where I put them. But where is the video by Helber? And the good thing is that I did look for it in the morning before coming here, so I know where it is. I can click on the 25th, and that's not the case. I can click on the 24th. Well, now I lost it apparently. So click on the 26th, that's lecture 7, that's not where Helber is. Maybe I go under 18, that's right. So the second lecture already was explaining, so far in the week, in the first week, you're going to get used to the environment, you're going to write some code. You will first try to use classical computing, that's Python, to do probabilities in 3 different ways, I guess. And then we will put together, we're using Qiskit, which is a library written in Python. We will simulate quantum circuits, and for simple qubits, we have no limitation of how slow it's going to be. But just like we were told, if we have too many qubits, a classical emulation of that is going to take a lot of time. So the video by Andrew Hiller is here. That's in the second lecture of the beginning of the class. And then there's a set of slides where you are going to find that he doesn't use any missing-state formalism. Let's see, that's what Diana Franklin does on LS at Chicago. But if you go in here, you can look for Deutsch, and you get a description of the Deutsch-Jurja algorithm, which is an algorithm that uses oracles. And our approach was to talk about, and now we're going to get started, those 2 papers that Ed Barnes and Sofia Economou put together that describe what they've done over the last 4 years with their summer class for high school students and young undergraduates. And the booklet that we were, the actual paper that we were describing, we went through it yesterday, and it's clear that it's stated that we will be using the missing-state form. They are using the missing-state formalism, and this is an approach of Deutsch-Jurja that is replaced with something that sounds more interesting than the actual problem. So if you look Deutsch-Jurja in Wikipedia, for example, then what you're going to get is problem statement is over here. It's a very mathematical description. It's not hard, but it's maybe boring. And I suspect that this particular problem statement would relate not as much with a high school student as with the game of money or tiger. This is the basic idea that if you have to determine whether a function is of one kind or the other, as described over here, just like in the case of Bernstein-Maserani, you will try a bunch of things until you get past the half of the domain of the function, and then you would have the answer. But then you would have to test because you don't know if the function is constant or symmetric. And if you get, 1, 1, 1, 1, 1, and then you get past the half and continue with 1, 1, since they told you that the function is either symmetric or constant, then you would say, this is not symmetric, this is constant. Now I know what the function is. So it's in many ways similar to Bernstein-Maserani. That one has 2 different stages, and the second stage relies on nothing. I mean, no mystic states formalism at all, because all of that formalism has given us a tool that's a high-level tool, phase kickback, that is in fact supposed to help us with this, with the algorithm. So I'm done with reviewing the topic here. I'm going to move to the iPad, where I'm going to say that if you look at the little qubit cell, I'm not sure if that comes up right away or not, especially if I mistake it doesn't, but then I guess I'll go to the syllabus. What we would like to do is to describe the actual diagrams and then implement them. So very soon I'm going to add information here in the notes. The red numbers are going to be the ULIS lectures next week. And then if you're looking into what's due, you understand that we have a notebook with Deutsch-Jurja this week. But you have what you had in the past listed, and then things are streamlined from now on because I have some topic, put the notebook for that circuit together. There may be more than one case. Incidentally, the video by Andrew Hiller is also including not just Deutsch-Jurja, but also quantum teleportation at the end. And we're going to come back over here and I say, look at the contents of what we have done so far. Number 9, chapter 9 is Deutsch-Jurja. And if you were to say, what are we gonna do if we do this Deutsche and it ends very quickly, let's say we do it today, or maybe do it tomorrow, and then we have Friday for what is the next topic that you are going to approach? I said that I'd like to do Grover search algorithm, even though what you see over here as the next chapter is super dense coding. So I'm gonna click on the Deutsche and maybe I'm gonna explain this too, and I'm gonna go escape. And I'm gonna say stop sharing. I got something in the chat. What do I have? Are these on Canvas too? All right. Who should be on Canvas? I am not entirely sure. So I think the question is about Helver's video. So number one, I think I should put Canvas. If you want, let me just go in. I don't know if I put them in. So these are free, and the website that I'm showing you, C290 Quantum, is also available to everybody. But there is a small part of the website that has resources which are available only through username and password. And not everybody has a username and password for network ID here. But everybody who wants to get into Canvas can. Now that Carla brought this up, this is very, I guess, serendipitous. And you're going to explain in a second. So I'm going to say that not everybody is in Canvas, and to my calculations, but I may be wrong. The only person who isn't in Canvas right now is Chris Combs, who I met in person before the class started. So now let me just quickly ask him, is that true? I see Jack, so I'm gonna write Jack. So Mr. Combs or Chris or whatever, would you be able to confirm that you are not on Canvas? And can you get on Canvas, or do you need any help from me?
I can check. I was able to get in Canvas before, but I wasn't assigned to the class.
Oh, that's good. Then I may have forgotten something. So I'm going to go to people, and since we go into Canvas, this is really good. If you have a IU email, or if you have created a guest account, you may have sent me the email and I may have missed that email message. So if I were to add you right now, what email should I use?
Christopher, CHRISTOPHER .combs @EVSC
BBSC.
CK12.com.
So this is, so I'm going to push the button next. And if this is an email that you registered for an IU guest account, it will find you. And then I would have to apologize. Absolutely. So I think this is my problem. That you did this and I got the information I suspect, and I wasn't aware of it. And now that's why you're the only one not in Canvas. So I'm gonna say, I will add you now. Sorry about this, and thank you, Carla, and thank you, Chris. So you are now pending. So that's the only person that I couldn't find. And whenever you can, please accept the invitation, and then you will be in Canvas. But Carla brings up a very good point. What is available in Canvas? Why do I go in Canvas doing stuff? So UITS was having issues with Canvas guest account, so they may have, or maybe I didn't do it on time. So, but thank you. So I'm going to go now and say, if you go into home, because this is a good point. If I go into home, I say, there is a list of class resources. I mean, you can go to the website outside, but you can click here and these are the resources. I have Dancing with Qubits, Quantum Computing by Barry Bird, Dancing with Python. And then I put some stuff here, which is in fact mostly free, but I still put them here. So there's the actual textbook, which is conventional math. There's a guide for young students. This is a physics book. And this book is going to become really important when the Oxford lectures are going to start. Then there is a free book for quantum computing for curious users or the dedicated users. This is a book that's not free, but I showed it in class and I like it a lot. There's a lot of exercises solved, not just answered. And then what I would like to add over the break, which is 2 days from now, is here. So in the process, I now have the answer saying, no, what I showed is not here. So I'm going to say, for example, what exactly should we add here? I'm going to say that what I would like to add.
If you have.
What?
Helgoland.
Helgoland?
Yeah.
Well, that's a book by Carlo Rovelli, I don't have it,
You
but it's a story. It's a story, it's fascinating, but it's a story, you know.
Okay, good.
Look at Heisenberg had allergies and he had to go there and he didn't know matrix mechanics and he had to invent it and then he came back and
Okay.
found Jordan Pasquale, who's a very horrible person, politically speaking, but knew math and stuff like that. So Helgoland, I don't have it. But if you say, well, we should, then I guess I will see if there's a PDF of it.
It's okay.
So I'm gonna click here and I'm gonna say Andrew. Helwer, slides. Andrew. Helwer. Okay, Helwer, LWER, and this is video. Then paper by I buy Mansinga. Booklet. And I'm not entirely sure if anything else is supposed to be posted here. I'm okay, so then I say I guess also, okay, let's go back and say I want, okay. All right, so also, oh, come on in. From week 3, we have these guys. I will put the dot here and that's it. So then I say more to come soon. I'm gonna say save. And no, I don't have them, but now I made a note. First of all, I did something really important that I added the last student that wasn't there. So thank you, Carla, thank you, Chris. And then also I wrote down this note for myself when I put all the others. I will actually add those two links. So if I go to C290 before I get started with the thing, if
Thank you very
yeah.
much.
I thank you very much, because I haven't finished it yet, but seriously, without you, I don't know what I would have done. So some 2022. And just so you know where the books are coming from, if you click on resources and you authenticate, but you can't, but I can, and a bunch of other people, and I'm gonna take these books. All these books are listed here. So if you say, oh, maybe this is an interesting book for me, I have the book. I will just download it and then upload it in Canvas. And I will absolutely do it over the 4th of July. So, so now I have a quick question for my self-control Shift H. Do I need to put the link here for the booklet or for the slides? And I am going to do the following. I'm not going to put the links for the individual things because I'm going to click on one, and I'm going to say that this is. Let me edit this guy. So let's pretend from week 3. I want to give you the link of the website. It doesn't need any password to know where the booklet comes from, for example. So I say this is a link, it's an external link, and I push the button, and now that week 3 should be there. But I'm going to say from week 1. In other words, there's something in week 1 that I just showed you, and you say, but I don't remember this, and I do much better with Canvas. And if that's the case, sure, let me just put the link here straight to it. And week 1 is this link that will take me to. What did we say? It's the second, and we said somewhere in here you have the links if you want, the way we presented them at the time. So I'm going to come back here and put the this is an external link, and I'm going to push the button and put this in. And when I'm finished with this, I'm going to save it. So if anybody comes to the resources and says, okay, he promised a bunch of things, hopefully we will put this quickly. You can use these links to go to those sites. For example, if you want a booklet, it's go week 3, and you have the booklet here, like we discussed earlier. And if you just want week 1, somewhere in here we have Helward, Microsoft, and the slides associated with this. And this is a circle state machine. So that's me cutting from his slides and presenting them to you. Okay, so
Thank you. That works.
you are very welcome. And I thank you once again, like I said. So I'm going to come back over here and I'm going to say, I am going to do escape and then stop sharing. And I'm going to share from this guy. Here is my pen. Oh, I'm going to say share content, say screen and start broadcast. And this will take it, I mean, I will start sharing the screen that I have from yesterday, which I'm gonna have to erase. And you remember that the thing that I'm sharing with you right now is the first two questions that we got at the very beginning in the lecture yesterday. There was a question from Elma saying, how do you justify that formula of determining probabilities when you have the outcomes? And I did it over here. I said, you have to consider the state as being unnormalized, and if you normalize it, then that means that the probability amplitudes are going to do the right thing, which is squared, added, they will give you a 1. Okay, so we said, okay, that's fine. Now in the process, you see how I have two whites and 3 black. Again, he doesn't use any numbers in his book. We could. And the moment we do that, we have to have a good reason. So right now, we don't have a good reason other than white really means 2 white, and my eraser is still stuck. Come on, eraser. But if we put numbers, then it's becoming easier for us to consider the actual state and how we want to normalize it. So come on, eraser, you have to shape up. Eraser is completely stuck. I'm using my pencil, doesn't get it. Whatever it's doing is going to wake up in a second. Okay, here's the eraser, and apparently stuff that I have in fact erased disappeared. Yeah, I can't do this. I'm going to say, let me make it very small so I can erase much faster. Oh, now the eraser also is scaled. That's all. So I'm going to tell you first of all that we start today the discussion of tue0702, and if we say, well, wait a minute, they say that they don't put any information there on the paper. So how do they do it? And does it work for them? So yesterday in the office hours, I said we discussed and we were skeptical that when they say we tell the students to do this and they do it, we were skeptical of the fact that all the students are able to do it. And my theory was that there is at least 1 or maybe 2 students that can do some or maybe all, and then the whole seminar builds off of that. Yeah, I'm having trouble with this guy again, but maybe not for long. Okay, I am good right now. So what I'm ready to get started. So let me make this bigger, and I'm going to erase this and then get started. So here's what I would like to say. Periodically, you have to know where you are, and I'm going to say that the purpose of this class is to give you quantum advantage examples. So we're going to say quantum advantage, and I am going to enumerate them so you know which ones we've done and what exactly is coming up. So the first example of quantum advantage was Bernstein-Vazirani. When I meet with people, I say, can you explain it? Some people can, some people can't. And the point is, if you can, then I will give you a short description again. The idea is that there is a circuit, combination of gates, and you don't know for sure what it is. And you want to find out as fast as possible. There is a simple configuration that classically you can find in 1 step. If you reflect that one, suddenly the classical method doesn't do anything for you. You have to try every single one. And fortunately, that is solved immediately by the quantum approach, which relies on phase kickback. So I'm going to say that the phenomenon of phase kickback is also fundamental, but it's like a subroutine in quantum computation. Now, the second thing that we do today is tue0702, which kind of reminds us, the Bernstein-Vazirani. None of them involve entanglement. So if you say, what have I learned that is working here for me or in the algorithm, for the algorithm, is superposition is what's happening in both cases. Somebody was saying, do you see phase kickback in Deutsche? And I say, I have oracles, and I'm going to indicate over here. And the oracles, the way I design them, they have control knots and Hadamard gate. So clearly there must be some sort of phase kickback in there. The next step would be Grover search. For Grover search, the idea is that I give you a random set of values and I ask you to find one that is important. So the analogy here is reverse phone book problem. The phone book is indexed. So if I look somebody's phone number, all I have to do is alphabetically by the name of that person. But if I want to find whose number some number is, who owns that telephone, there is no indexing associated with the numbers, and all I have to do, I mean, all I can do in a classical sense is to go through all the phone numbers listed in the phone book until I find the one I'm looking for, which I've been told is in there, or maybe it isn't, not even there. See, nobody has that number. And once you find it, then you say, this is the name associated with it. So the thing is unstructured search. And you get a significant speed up. Instead of looking through all the entries in the phone book, you only need to look through square root of n. The next one that we are going to do is called super dense coding. And the name sounds good, but this is an entanglement protocol. Good, it's the first one where entanglement makes some waves here, like it's making a difference. It is also a protocol for communication. Everything that I wrote so far can be easily described with MISTY states. So the regular MISTY state formalism includes and supports this. So this is a regular MISTY state formalism in Q is 4.2. What that means is that I have little circles, white and black, and I have no numbers anywhere. Even though I could put the numbers, I don't have to. The fifth one says quantum teleportation. So we have to describe when the time comes what exactly it's about. It's quantum teleportation of information, not mass, right? So of information, not mass. I mean, clearly not mass, but I mean, we're not talking Star Trek and stuff. So quantum teleportation is also based on entanglement. And I would say that it's a dual phenomenon to super dense coding. So I will just say dual to 4 super dense coding, and I'll explain that at the time. The only thing here that we teleport arbitrary qubits. So now we have a problem. We cannot describe arbitrary qubits in the MISTY state formalism. Therefore, we would need an extended MISTY state formalism to capture that. The next one has the same problem, which is the GHZ game. We were told, you know, kind of like CHSH. We were told CHSH, we were shown by John in the first guest lecture in the first week that you could implement CHSH game with Mathematica. This also requires, for example, I guess the S gate, which means an I, which is equal to the square root of -1. Also change of base. And you would say, what do we do in GHZ? I'm sorry. GHZ is a state of entanglement between 3 qubits. So entanglement is also important here. But it's not really a communication protocol. It's just a proof that nature is quantum, which means more than what we think or can do in a classical sense. So in the GAZ game, you win every single time, 3 people or 3 entangled qubits. In a CHSH, you can win 85% of the time, 2 people, 2 entangled qubits. Classically, you can only win with a predetermined strategy 75% of the time, which means that in the quantum realm, something is happening that we need to capture. Now, that part is not really included in our lectures in this class, but Maria could basically talk to you about it. It's an aspect of philosophy, and you can find it in Qs for quantum. It boils down in some sense to non-locality and the fact that reality isn't there as you measured it until you measure it. And when you measure, you know, there's a probability aspect associated to it, which means that you don't know what you're going to measure. You know the probability of getting one or other outcome.
But is he had said not we have this the Bell gates, is not just Bell gates with more than one, with more than 2 qubits.
Yeah, Bell inequalities. And again, this is in the book, and this is about the philosophy of it. Like, what does it really mean? But then this gets into the interpretation of quantum mechanics. There are 6 or 7 of them, and various physicists, high profile, they disagree on what the interpretation is. But then you go and watch David Deutsch's video from 2006, which we wrote down. We transcribed them, and he says, "Look, I'm a firm believer in many universes. And you may not accept that. And I just want you, while you watch these videos, to assume that it's true. You see that even if you don't believe in it, it's the best formalism to think about these things." So what we have over here is our description. We are now in Deutsch, Georgia, right here. Percy Vasily in Deutsch, Georgia, no entanglement. Rover search, also no entanglement. Supertest coding, quantum teleportation, and GAZ, yes, entanglement. These two will need, I'm gonna go and say that for these, we need extended misty state formalism, misty state formalism. All right, so then when you finish this class, for example, and somebody said, "We don't have much time, just tell me what you learned." You could easily say, "We learned an aspect of computation that is non-classical. That involves phenomena such as superposition, phase, interference, and then specific gates, you know, what qubits are, which are really not classical bits, and then gates of 1 and 2 qubits and circuits that produce phenomena that that are fast, so to speak, or they cannot be described in classical sense." And now we go to Deutsch Georgia. So I'm going to erase all of this because it's on the video and I can get a slide of it by a screenshot at any time. And I'm going to remind you of the game that we have and how we're going to put together the. I lost the eraser again, but now it's coming back, so everything's good. For the game that we are playing, which is really an implementation of Deutsch Georgia, we have the following situation with black over here. There are 2 doors, and the doors are labeled white and black. But in between the doors, there is an oracle. So doors, 2 of them. One has a white circle on it, and the other one a black circle on it. There is an oracle. An oracle is something that you can ask questions. And I'm going to describe the behavior of the oracle. It looks like this. So I'm a little bit uncomfortable about one aspect. Normally, I run the lectures off my students, basically. So I would like at some point to bounce ideas off John and Elmar, because they are here, but also online if anybody wants to participate, that's also. So the oracle is going to say, "Please put a test qubit here." And the way you put it is always black. And then there is here a qubit that says which door you're asking about. And so you're going to put either white or black. Then what comes out of here is the qubit for the door that you put in. This comes out unchanged. You asked me a question about a door. It could have been white or black. Is this? I only have 2 doors. And if you put door qubit there, white or black, it goes to unchanged. That part doesn't change in the oracle. This is the oracle. As far as the test is concerned, the answer here, right here, white means yes, there is a tiger, watch out. And then black, which means unchanged, means no, you money, unchanged. This means money. All right, so you have these two doors, and there's an oracle in between, which looks kind of like this. And the problem is, please ask one question, and then either open both doors or close the doors. Just one question. And in the classical sense, allowed. Okay, in the classical sense, you need, I could say, either I say up to 2 questions. If the first question, it's like black door, do you have a tiger? No. Okay, I can't stop here. I have to ask about the other door. And in general, on average, I would say on average, 1.5 questions. All right, so sometimes I ask the question, they say, yes, there's a tiger there. Then I say, okay, bye-bye. I don't need to ask the second question. This is dangerous. I leave. But sometimes you have to ask the second question. So on average, you have to ask 1.5 questions. And the trouble is that that's bad because you have only one question. So in the classical sense, you are in trouble. What we are going to do now is solution, quantum solution. So the plan that we have is, let's describe a solution which will be able to solve this problem. We ask one question, carefully formulated, and the answer comes back and we are done. We know if we can open both doors or not. One question is enough. But you have to be careful how you are asking the question. In some sense, this is, I said before in office hours, maybe even in class, it's like the uncertainty principle, because in the uncertainty principle, if you know where something is, you don't know how fast it moves. And if you know how fast it moves, you don't know where it is. So then here you're going to say, I'll ask a question and I will know if there's a tiger, but I don't know where. So I do get something with 100% accuracy, but then the other part is 0% accuracy. I really don't know where the tiger is. I don't care because I'm going to open both doors. If I do open both doors, and if there is a tiger somewhere, I don't really care if it's coming to eat me from the right or from the left. Both of them are deadly, so I will not open the door. So that's the basic idea. So what are we supposed to do? We have to write a quantum circuit, but before that, I'm going to say here, let's design the oracles. So there are 3 cases. The first case is no tiger. And the second case, I'm going to follow what I have in the qubit set. I think I put second case is tiger behind white door. And this will be on page 29 in the qubits thing online available PDF. And the third case is the tiger behind the black door. Okay, these are the 3. And so this is what we would do. If they claim that they have, in fact, asked their students back over at the Virginia Tech to solve this problem, and they say, this is how you do it, go ahead and do it, show us the answers. I genuinely believe I'm skeptical of saying, like, I don't know, they have 20 students, so 15 are going to solve the problem. Maybe they do because they talk to each other, and if somebody knows, they start teaching and the information spreads in little groups, perhaps. But my experience with similar problems was that, to my surprise, every year when I ask a hard question in class, I know this is a hard question, and yet there's always one person that kind of has the right start. either solves half the problem immediately or sometimes the entire problem. I don't know who that person is, but there's always one person in a class of, let's say, 60, for example. So that's a surprise, always a surprise, but a pleasant surprise. So maybe they have the same situation. They bring this up, somebody says, oh, I know how to do it, or I think I know. And from that person, everything then spreads because they probably, Ed and Sophia, they say, okay, that's a good idea. Well, how would you do this? How would you do that? Now, in our class here, we can't do that. Because here, I'm going to bounce ideas from those people who are here. But how would you do, for example, John, an oracle that is like this guy? So I need something that works operationally like this. And how would you write an oracle as a quantum circuit that will have the following behavior? If you put, let's write the behavior. So first oracle, no type. What is the description of inputs and outputs? I'm going to say, for the first oracle, if my input is over here, right? And then what's the output? I have 2 qubits. So I should have 4 inputs, but really 2 of those 4 are not useful. Which ones are not useful? Which inputs I will never consider?
The ones where the test input is white.
That's right, the ones with the test input white. We don't use it that way, right? So the 2 possible cases are going to be, or both of them with test qubit is going to be black. Great. Then the question is, what is the value of the other 2? I mean, the second qubit in the other 2 cases, in these 2 cases. So I'm going to go to Elmar.
The doors,
What?
the doors.
They are the doors, which means that the values are going to be
Right.
either white or black. So I'm going to have to make this one black. And listen, for an oracle, any oracle, I'm going to have these 2 inputs. There's no other input. So now I have an idea. Go back to eraser and say, I will put the input here, but I'm going to put the input for all oracles. So I'm going to come and say, here's the output for oracle 1, oracle 2, oracle 3. So this one here is no tiger. This is tiger behind white door, and this is tiger behind black door. So these are all outputs. So what is, go back to John now. I could go with people online, but now I'm just going to go to whoever I see in here. And people online, if they say, I want to participate, then stop me and we will discuss. But it's just go by of John, and that's also not a bad idea. It's going to be a little bit faster. So John, no tiger at all. Black, white. Black is a test. White is the question I'm asking. What is the answer? So what am I describing? I'm describing the test qubit, correct?
Yeah.
So unchanged test qubit. It was black, it stays black. That's the answer, there is no tiger. But what about the white qubit that represents the question that I asked about the white door? That also stays the same because those qubits stays the same, period, right? So what happens when I do the second one? The answer is there will be no change in the test qubit because there is no tiger. And there will be no change in the qubit that is asking about the door because they never change. Which means that over here, the second qubit is going to be white and then black. And likewise over here, I'm going to have white and then I'm going to have black. So these are the truth tables, but I still have to put, I'm going to ask Elmar right now, in B, where the tiger is behind white door, what does the first value look like? For example, here I'm going to say,
It turns to white.
right here. It turns to white, exactly. It starts by being whatever I have over here, right? And it becomes white, absolutely. So in the case where I put black, white, when there is a tiger behind white door, I expect the oracle to respond with white, white. Because the answer is, yes, there's a tiger there. If the tiger is behind white door, then it's not under the black door, which means that black, black remains black, black. Back to John, I'm going to say, what if the tiger is behind the black door? What is the output here?
The top one. Oh, there it's white.
that is correct. The test qubit is going to change. But in the first case, I put a black, it comes out black because the question is whether. The question is whether there is a tiger behind a white door, and in this particular situation, the tiger is behind black door, therefore, for this, right, here. The answer, when I ask, is there a tiger behind white door? Is there a tiger behind white door? The answer is no, this is a situation where the tiger is behind black door. And therefore, when I ask about the white door, the answer should be no, it's not there. It's here, it's right here. So these are the truth tables. And now I'm going to have circuits that behave like this. I'm going to do this, for example, see, okay, so this was there and now it's much smaller. So how can I describe the circuits that behave, for example, like this one here? I'm going to use this marker, this circuit here. So let's go to John. Which circuit will give me that behavior? Black, white stays black, white, and black, black stays black, black. Just no gates at all. Exactly, 2 wires. Now I'm gonna say, I have a problem, Q0, Q1, right? And if I do this, this is the circuit that I want. But what I was told by Watchers is that if I rotate, I can't rotate it, right? I cannot rotate it like this, I just move it around to translate. So he says, rotate it clockwise, then I will put it like so. And this down here is Q1, and this is Q0. So this is a good circuit for the oracle where there is no tiger whatsoever. Whatever 2 qubits I put in, that's what I get out. Whatever 2 qubits, black or white, or black and black. And this actually, I'm going to have to erase it. That's the right thing, but for this guy over here. So the oracle is this. Where I say this is Q0, and again wrong. This is Q1, and then this is Q0. So now, how exactly am I going to do this thing? Maybe I'll ask Elma. What is the circuit that will transform? Let me write it over here. The idea is that if I put this in, I should get white, white. And if I put this in, I should get black, black. So what's the circuit that does this? Okay, he's thinking.
It's not a C-note,
Well, it depends. So if you've never designed this,
but the C-note turned around.
so if you do not know, if you haven't done it, then you need some attempts. And we decided we're not gonna stay here and think, because that might just take forever. So I say, all right, you thought about it. I bet you thought about it yesterday too. How about we write down the equation, the formula, the diagram that we have in the book, and then see if that seems okay. So I'm going to say, here's a circuit that is tiger behind white door, which is really what we are dealing with here because of this. See how the test qubit changes when the second one is white? That's the question. Is there a tiger behind white door? The answer is yes. Well, then that's the situation we're dealing with right now. So here's the circuit. Now, what we have right now, 2 wires, it's not good because the 2 wires are good oracle for nothing, no tiger whatsoever. But if you look into the middle thing over here, I'm going to say that there is a NOT gate on Q1. And then there is a control NOT with a control on Q1 and the NOT gate. Just so you know, remember that the plus is a very specific symbol for a control NOT. But that's because the plus itself in a circle used to be the symbol for the NOT gate. Now it's X. So this is a NOT gate. And this is a control NOT because of the control is a little dot, and then the gate being controlled is the old symbol of the NOT. And then say, okay, good, no problem. And now what I have is, my goal is to understand these circuits, not to invent them. I mean, somebody did that a long time ago. And yes, the high school students apparently at Virginia Tech are coming up with these answers themselves, and you too, but they don't tell us how long it takes and how the dynamics is happening. So our plan is, let's look at what I wrote in the qubitzer and see if you think that that's correct. So after I do the 3 oracles, then we want to establish the circuits. There's always the same method for that. And then we would like to verify that the oracles and the circuits are working well. And then we implement them in a notebook. There clearly will be 3 circuits. And we would like to verify that each circuit representing a specific situation with respect to where the tiger is, nowhere, under the white door, behind the white door, behind the black door. Then when we feed input in those 3 circuits, we get exactly the right answer with respect to the one question that we ask. And there's enough information in the output to says, go away or open the doors, you can get all the money. So now back to John, I'm gonna say, if I have this circuit over here that you see, for example, right here, how would you prove that this circuit is in fact a good oracle for the situation where the tiger is on the behind the white door? That's right. We have a strategy that says feed the inputs and then propagate using the Mrs. State formalism and see what you get on the output. And we have a simple system, a rewriting system, anybody can use that. I propose the following. I propose that we come, so we say, sure, that's a good idea. I propose that we look in the qubitzer and see the third one seems to be easier. How about we do that first? So I say, let's look at this one here. So this whole thing is basically B, and now let me do C. And basically I would say, I look at Elmar and I'm gonna say, C says that if you enter black, white, which means that I have a test qubit and I'm asking you if there is a tiger behind the white door. This situation is the tiger actually is behind the black door. So the answer is going to be the test qubit does not change because the answer is no. And the door qubit doesn't change either. And this is what we got here, right? Then the second part is I'm going to ask the same question, is a test qubit that's black? And then I'm asking this about the black door. So please tell me if you have it under the black door. But this is we're describing here is the tiger is behind the black door, which means that the answer is going to be yes. Danger, Will Robinson, blah, blah. And here we say this comes back as black on account that the black is about the door and out comes with the color that you were asking about. So you are concerned over here. So what will be the circuit over here? It's going to be 2 wires as before. Only if you look into the qubitzer, we have this much simpler oracle. The simplest oracle was right here with no tiger. So I'm just going to say no tiger. Okay, the next simplest, yeah, well, I should have done that, but I can. Yeah, the next one is going to be right here, apparently. That's an eraser, so I want this. So it's going to be something like this. Hey, here's a simple oracle that has, this is Q0, no, Q1, sorry, Q0. And this is tiger behind black door. That's the situation. So when I started saying, come on, show me that the thing is working. Yeah, we can try the middle oracle, but that has 3 gates. And if there's something simpler, we would much rather try that. So, you know, I could go online to Carla, I could go online to Alisa, or who was number 8? Sorry, I missed somebody. So I'm gonna say participants. Did we lose anybody? Jack, I forgot to write Jack. Okay, sure. There you go. Okay. So I can go to Jack and I can say, Jack, would you please be able to tell me if this description matches the oracle? And I don't know if Jack is available. He may or may not be. I mean, let's just see if that's the case. So Jack is not available. That's totally fine. I was going to say that perhaps, so I go back to John, because John is right here, Elma too. So I'm gonna say, let's go back here and ask ourselves if this is the case. And exactly.
Turning right.
Yeah, Elmar is describing with his hand how you do things. I absolutely agree. What we have here is this, X like that applied to black and white. So my question is, what do you guys think that is? And the control here is on the right, and because it's white, nothing happens.
So not.
So that's exactly this guy. We start with black, white, where the white is the control, then we get black, white. Okay, that sounds good. What about this? I have a control knot and the control bit is on the right. That's what the arrow says. So when I put black, black, oh, the control bit is in fact black, so the other one will change. That means I have white and then I have black over here. So yes, that's exactly what I get here. Oh, that's easy to prove because it's just one control knot and it's from right to left. So I think we can easily say, yes, this spot was perfect. I mean, this works. We can then say here that this oracle is exactly what we wanted. So now we have two options. Either we go with this oracle that's better than the empty oracle, and then verify that the entire circle works well, then maybe even implement, or go and work on the third oracle. So my idea here would be, I think I'd like, because it's 9:46, I'd like to work out a finished instance of the problem. So I'm going to first say, look, this is the whiteboard or whatever it is. I'm gonna take the eraser and erase everything. You in the video when it's posted in about an hour, 2 hours, you can stop the screen, take a shot or whatever, copy it on your notebook, and then you have it and use it. So I think when I drop the eraser, something bad happens. It gets confused. I should never drop the eraser. Because look what's happening. So eraser, please wipe out everything. And now our goal is to go in. This one is the thing. I'm gonna go over here. So let's work out the complete solution for these two oracles that we have seen. So no tiger whatsoever. The entire Deutsche. So we know that the oracle is like this. That's the oracle. But as they told us, and then I'm going to say, sorry, this is a Q1 and this is Q0, just so we know which wire is which, because if I really have to do it in the Qiskit, it's going to end up like this. So let me write it, I guess, both places. This here is a wire, and this is another wire, and this one here is Q0, and this is Q1. And I have to do this on account that, yeah, well, I wanted that, but now, okay. So I'm going to go here and erase this guy and then put this here and see how much thicker that is. Okay, that's thicker and this is thicker and so on. I'm going to try to do this both ways. So if I do this, I'm going to say Q0, stay away. Because I'm going to have to put something in there. Maybe this is too big, but so then what's the basic structure of the solution to this? So I'm going to say, listen, let's do things completely once, and then let's discuss the Qiskit aspect of it. So yes, I have an oracle that looks like this, but they have told us that whatever oracle I have, let's say this is the oracle over here. This is the solution. I have to put a Hadamard gate here and a Hadamard gate here. And the oracle, as you remember, has 2 qubits input. And out comes the answer. And you get H on each qubit to restore what you had in the very beginning. So this is the general solution. Am I actually? Okay, I'll go with this one. So this would be the general solution. Okay, so what's the solution again? I'm going to use this as the oracle. And I'm gonna have to put a Hadamard gate here and a Hadamard gate here. And then I have to put a Hadamard gate here and then a Hadamard gate here. And this is great because this is the simplest possible situation. So we'll do things to a certain extent so that if you want, if you have time, I understand you may not. But if you have time, then if we finish this, then you can do it for all three for tomorrow. And then we can implement all three and we're done completely. So if this is the full solution, I'm going to erase it over here because I'm going to try to describe what's happening here on the left by tracing what's going on. They told us that the solution now, the question, this is not tiger. The protocol has changed. So protocol has changed. Now, how? We used to have an oracle and the oracle still behaves as such. We just tested it. We put a test qubit and a door qubit. And if there is a tiger there, then the test qubit changes, otherwise not. So the protocol for our one question, know if it's dangerous or not, is this. Always feed 2 black qubits. You gotta feed 2 black qubits, that's the answer. The inputs are always, I meant 1, which is the same as black. Okay, so many money says, I don't understand what you're doing, or I disagree, you tell me, and then we will discuss. The answer comes out white on the right if there's a tiger somewhere. So first thing is that inputs are always 1. B, well, I guess I don't want you to think that these are the A and B from before. So I'm just going to say the first thing that has changed is that the inputs are always 1. Well, that's the protocol for the question. The second thing is, actually, it's not good to say that the protocol has changed. In the past, in the classical sense, we never had a circuit. We had an oracle, and we would ask the oracle 2 questions. We never had a circuit. So I would say that the protocol has changed in the sense, here, this guy, that we have a protocol now for the entire circuit, which in the beginning, in the classical sense, we never had. This is the protocol, so come on. This is the protocol for circuit. The circuit uses the oracle inside. You put 2 1s, right? And the outputs are going to be white, which is this, on the right, if there is a danger, tiger, somewhere. Tiger somewhere. The tiger somewhere comes in here, tiger somewhere. Well, okay. All right, if you agree with this, I mean, you understand, says, if I were to take the oracle separately, we already know how it behaves, this is the simplest oracle too. Then I make the big circle, the big circuit out of it. And I'm going to say this is Q1 and this is Q0. So this will have an impact on how I code and read the things in Qiskit. But this is, by the way Qiskit would read like this. So making it vertical, it just perfectly matches what we do here, which will mess up a little bit our way of calculating with Mr. States. Because our calculating with Mr. States goes like this. I have a peak box followed by, the oracle, and then I have another peak box over here followed by the oracle. The oracle has nothing inside, so I just go through regular wires into peak boxes at the end. And I already said this is the protocol. So here I'm going to do Q0, Q1, and if I want to write down the answer in Mr. States, my order is always Q0, Q1. But then if I do it in Qiskit, I will read Q1, Q0. So this is like Qiskit and ordering, and this one here is Mr. State formalism ordering. Is like that. Boom. So once again, what are we doing here? Well, put 2 black things in. And I have oftentimes this. This is the state at that slice. I put black over here. And then black over here. So here the state is that. Now in our circuits, I gotta be careful, we don't have by default black input, we have white input. So if you truly need the black, you have to put some X's there. Both on both sides. And then what is the situation over here? I put a dotted line after, say, the first H on the top. Because I just want to describe what happens there. There's a white and the black with a face. That's what we get from a Hadamard if you put a white, a black ball inside. Then if I just want to describe this part over here, I have the exact same thing. Then if somebody says, fine, thank you, but can you describe, as a matter of fact, let's say, okay, these are two different things. Please don't combine them, but now as they say, do combine them. I want you to describe not what the first Hadamard does to the first qubit and the second to the second qubit, but rather tell me what the state is here. What's the combined two qubit state for what comes out of the Hadamard gates? And the answer clearly is this. The first qubit is that. And the second qubit is that. We discussed this before. I don't know why that, sorry. So back to this, come on. Okay, so now if people say, well, can you tell me more? Basically, you can unravel it. This is not an entangled state, so it's factored out. And you can say white, 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 black with a face, black with a face, white, and then black with a face, black with a face, which is black, black. But we don't need that because we can just say, let's stay with what we had. That's the best way in this case. So fortunately, we don't have any entanglement over here, so I can continue to think of the two qubits as two independent systems. So on what is that? I'm sharing the screen, yes. And what have I destroyed? I think I lost this guy because I put my hand on this guy here. See? Come on. Wait, this is strange. Do you see this guy? Okay, it disappears. Come on. Why are you disappearing? Anyway, I don't know why it disappeared. So I put this guy somewhere else. And I clicked on it and it switched the thing from it. So this guy was a puppet, but apparently now it doesn't render anything. So I'm going to come over here and says if it's equal. Why is it not ever? What? It disappears instantaneously. I don't understand why this is happening again. Connect is wrong. What does this mean? See, now I lost, every time I write something, it disappears. What is going on? Geez, this is very annoying. I don't know. I press something and turn, whereas I write something is actually disappearing. So see, come on, stay. It doesn't stay. Immediately disappears. Why? What is that? Where is Shiva to help me? Draw with finger. I don't want to draw with finger. Pencil settings. God knows what's happening right now. Show effects when using scribble. Left corner swipe screenshot. Right corner swipe. Left corner. I have no idea what is going on here. Well, that's a disappointing moment. But I'm gonna come back here and says, this was so great, and now it's working. Okay, everything shows up. Who knows what I did? Let's quickly stop creating situations. So disappear. Doesn't show the eraser anymore, but at least hopefully it's going to draw. So I said this is the culprit. See, it doesn't show me as I draw, but it shows it at the end. Okay, fine. I'm gonna have to organize this. So if people were to ask you, move this somewhere else, and in fact, I should just drop the video here. Video, come on, stop video. Okay. So if people were to say here, what eraser, man. I need to practice this, so I put a curly brace over here and I say, you can start saying this is white, white. And then it's what we decided earlier, I say you can do this and you put this thing with the. And so on, right? Okay, so I propose that we actually write the states like this. Because this is clear, and although I got this into this weird situation, clearly the answer at the end is black here and black here. And we just proved that the first case where there is no tiger, one question tells you that there is no tiger. And that's the end of the Georgia for that case. There are two more. There is an oracle that's somewhat simple. When the tiger is behind the black door, we work that oracle out. I would like you to at least consider doing this for that oracle. And then there is an oracle that we stated, but we never tested. That's when the tiger is behind the white door. And of course, we would have to go through the same steps for it. So in some sense, at this point, our treatment of the Georgia, manual tiger, is complete. There's still something left for you to practice, and then I'll show you the finished product tomorrow. So that's the end of today's lecture. With a little bit of problems on the iPad where I really have to become a better, whatever the name of this guy is, freeform person. So I'm going to say now, let's see, let's go back to Zoom. I say I'm going to stop sharing. And I'm gonna come back here with a video, start video, and I'm gonna say, are there any questions? Anything that you would like to know before we stop recording and disconnect?
Yeah, I don't know if it's been recording, but I feel like the average number of questions for that would be lower than 1.5.
Okay, that's fine. I said 1.5 because I said I either find in 1 or I find in 2. And I just said 1 + 2 divided by 2.
Yeah.
So it could be 1.25. Still bigger than 1.
Yeah.
Okay, now the question is that John is proposing the following question. What is 1.5 that I told you on average needed? Or the number is actually different? So here's a question to think for tomorrow, classical question. How many questions do you really need on average to answer, to find out whether the tiger is there or not? Good, that's John. So if there are no other questions, let me know by email or in office hours if you need anything. Otherwise, I'm gonna stop recording right now and I look forward to see you tomorrow with the wrap up for this lecture. Thanks again.
Why is it's not 1.5?
Because there's more possibilities where you would get to run away on the first question.
Let me do a brief.
2 cases you would get, you don't have to ask a second.
Oh, because we don't have the tag case, that's what it's.
How about-
Yeah, because there's no tiger.
So how about we put this in the recording?
Okay,
So then, what is the number that you think you have?
I think it's 1.33 repeating.
Okay, so the class is over, but we had this video here. I guess.
The chat.
Yeah.
But on the other hand,
Where is
you
it?
open a door, right? And it can be a tiger or not, right? This is the first question that you have. And then you have to, and with this first question, right? It's 50-50, that is a tiger or not a tiger. You don't think it's 50-50 that is a tiger or not a tiger, that's what you say. When you open the first door. Right, so this is the first question.
Oh, yeah.
So now we have the thought, basically, this is a discussion, right? The discussion kind of seems to include that my simple-minded calculation may have been correct. So let's see if John can summarize something that he's happy with based on what Elma said. So there are 2 doors and the tiger may be nowhere or maybe under one of the doors. How many cases do we have? 3. 0, 1, 1, 0, 0, 0, let's say. Like 0, how many tigers you have? So if I pick the first one, in either one, I could be lucky first, but then you said, what's the chance of that? So I could pick the tiger one, or I could pick the other one, and that's gonna be 50 overall. In all three, I could randomly pick the tiger door and say, is there a tiger there? And in two of those cases, I'm gonna get a yes. And then, okay, those are the good ones. In the two, but the third one, I'm gonna get a no because there is no tiger whatsoever. Now I have to ask a second question in 2 out of 3 cases. That's why you were working with 1.1/3 or something.
Yeah,
So in those cases, actually. In all cases, I have to ask, so if, okay, the two cases, well, I don't want, I should have left John or Emma to say, but now I'm speaking and I can't stop. So, pick randomly, there's a case where whatever you pick, you have to ask the second question. And there are 2 cases where you could randomly pick the tiger, and then that's the end, that's where you get a save. And in the other cases for those 2, you will have to ask the second question. So then you count how many you have and say these are the total number of questions that I have to do. Answer divide by 3, and you get the average.
I mean, if tiger and money are not 50-50 seeded,
They are 50-50.
then you come into having other distribution than 1.5, right? But
This is a good point. So remember what John said. We give you a problem and we say, is this fair? And it turns out it's not fair. How can you make it fair? So John, usually
Yeah,
change the payoff. But John says, how about we distribute the chips differently, makes you very rich. Then if you have a significant reserve and they don't, then yeah.
But then he as well said the game goes for 100 iterations, right?
That's
You
right,
expect like the number of
That's right.
iterations, yeah.
So Elma says, is it possible that the tiger is under a door or another with different probabilities? And the answer is no, it's completely random. The tiger ends up somewhere with some probability. There are 3 cases. One has no tiger, the other one with equally likelihood black or white. And we don't have to take the time to solve this now, but we have 2 competing ideas that 1.5 may be right, or maybe we have 1.3. Now that we looked at it, maybe 1.66.
I think it's 1.66.
So it's worse than my 1.5.
Because there's only. You can just look at it as, there's only one case out of the 3 where one question tells you that there's not.
The point is there will be 4 cases, but we don't say 4 cases. There would be the tiger case.
We don't have a second tiger, yeah, one tiger is enough.
But it would exist. It's like you,
Yeah, that
like
would-
your seeding is done because you say you always use something on get, you always use 50-50. There would be the case that 2 tiger exists, but you somehow don't mention that one.
Okay, so here's why this question is relevant. I don't mention it, I don't allow it, by the way. But then your point is, what if that's a possibility? So for Grover algorithm, the situation that we're gonna solve is this. There are 4 cards on the table face down. One is a queen, the others are numbers, 2, 8, 4, whatever, 6, 5, 7. Your goal is to find the queen. Question now is a little bit harder, but of the same nature. How many cards do you need to turn on average until you find a queen? Like you could be lucky on the first try, but if you didn't find a queen on the first try, you have to turn a second card. And if you got the queen, there you go, in 2 tries for that situation. But if you can't find, try the third one, and if you try the third one and you didn't find a queen, it's clearly the 4th one. So the question is, how many cards do you need to turn until you find a queen on average, considering all cases? So, you know, we have people like 2.5, 2.125, various numbers, and it's interesting to calculate. I'll show you a book with a number and you may dispute even that book, that number. But the basic idea is that you choose at random, you don't know where the queen is. Well, there's the key. How many cards?
Is it at random? Because
It is random, but
you know when the
but the Grover algorithm needs to turn face up only 1 card. And 1 try finds and I hope you find that hard to believe.
Yeah.
I mean, but that's the speed up. Yeah. So Thank you for the question, because we're gonna have to revisit it.
Yeah.
Slightly more
Yeah, it's a
complicated.
good question. I'm really
Absolutely.
and I'm not sure about my answer.
And I'm glad the probability increased.
Yeah, it's even more impressive.
It's called inflation.
I tried to simulate the advantage with Vazirani
Yeah.
algorithm, but I don't think it works to simulate with using Qiskit. Cause,
We did
cause
it.
does it actually simulate? Like if I'm timing it, like using runtime on the computer, I feel like it's gonna just take as long as testing each qubit individually. Right, because it doesn't really
Oh,
have the
that's an
capability
interesting
of
point.
using
That's an
qubits.
interesting, that's it. So nobody says timing. Nobody says timing. Count the number of operations. Right?
Yeah.
And you're absolutely right. If I simulate it classically, I will end up having to go through those because that simulation is classical.
Yeah,
So if you were to time it, then you don't see the advantage
Yeah.
because it's still classical.
yeah,
But
But
will you not have use just more memory, but you're doing less steps?
that might be, it depends on how it's implemented.
But yeah.
Yeah, so then for him to say, I want to see the advantage in time units, okay, then bring me some quantum hardware.
yeah, sure,
Yeah, so you could sign up for IBM
yeah,
and then you can
Yeah.
send it to a real.
The only thing here is that the time to send and wait and get the answer back is far bigger than the actual time.
yeah.
But they can tell you how long it took on the
Yeah,
CPU, I suppose.
Mhm. And the advantage is more when there's more
Exactly.
qubits
Yeah.
and you can only probably use a limited number.
They have I don't know how many they will give you, right?
Probably like
But they'll give you 100, well, right now, yeah, probably.
No,
it's
they only
like
have like
3,
1,000.
5. They do have 1,000, I'm not sure that's available to us, so.
Okay, yeah,
So I know that I was on the IBM page and usually you get on the copies of 128
Mhm.
or 27.
Okay, that's pretty impressive.
Qubits if you want to, so you can have over 100. And there is one that even have more 140 something, and it's a newer one, but it's in Toronto and it's locked. So the one that we can use free, we have only 128.7.
It's gonna be crazy when they have trillions. And we're like, remember the days when we were getting single
Yes,
qubits,
but the problem is
counting
that
each.
you have still a high error. And I think the problem is much more, even if you do a calculation, you have to look how much error you have, because sometimes you have 2% error, 3% error, which
With the
I mean,
measurements.
just with the hardware that we have at the moment, it's like, I think it's like in the old days when you had the tubes, you're not yet by the transistor, when you really can do your calculation, it's still somehow in it's my feeling is we are still in this time where we not have that great hardware. I mean, it's not only the number of qubits that you have, it's as well of how much error you have in one qubit
Yeah,
that we have to look at.
well, wasn't it the same with classical?
Yes, because
At the start,
qubits-
'cause
the
once you
qubits was
have enough, then you can start to use some for error checking. And. But when you only
That's
have
one
hundred
way,
and
but
twenty-seven,
the point is if we have a better hardware, then we not get that much error, right?
Yeah,
I mean, I just think,
well-
I think that material science and these physics guys will at one point get used to that we have something like the transistor that replaces the tube, and at the moment we have still the tube.
Mhm.
That's what I hope, but
probably,
I don't know, I'm not a physicist, I'm just a dreamer.
So it's like Wright brothers. I mean, flying at the time was a big proposition, people were questioning it and, they just flew a few hundred jets.
Mhm.
But flying right now is just completely reliable, I mean, there are accidents, but nobody cares.
yeah, and we have
We just
supersonic
go-
jets.
Exactly. So even with the internet that we have today, in the beginning, it was so hard to get that connection
Yeah.
on the west coast. And it would fall, it would break every single hour. So, the progress, I guess, is inevitable, it's surprising already where we are.
But that's,
It's
I mean,
20 years we know.
it's research, right? And sometimes it takes just time, right? Of course, you have to put money in, but sometimes people think when you want to research it and you talk to people from the road, they say, but but we have now given so much money, why you have no solution for cancer? I'm a
Yeah.
cancer researcher. Well, 60 years ago, we didn't even know the structure of the DNA. So we are very fast with making progress, right? But this, we cannot solve the problem physics, they make physics for hundreds of years. I mean, that they came down to the quantum.
Quantum, quantum theory has only been,
Do these experiments, but in biology, we don't have to have that much time. Okay, now I'm
Yeah.
in my field. And I think in quantum computing, it's a bit the same, right? This computer just need a little bit
Yeah.
more time.
even, isn't the whole thing though, that even they think once we have fully functional, good quantum computers, it's still not gonna be used for everything?
No, it's not gonna be
That's
better.
Because some things will be better with classical.
Yeah, it's
still.
like accelerators for graphics. And some of the things that you do with accelerators for
Yeah.
graphics are not applicable to the other things you
Yeah.
do.
For different types.
Yeah.
So with the super dense coding, can you use a quantum computer as
It's a-
classical, but with,
Super desk coding is communication. So I want to send you, using one qubit, I want to send you more than one bit of information. Because if I give you a qubit, you measure it, you get a bit, right?
but you can't use the one qubit as multiple bits of processing.
How would you? I give you a qubit, it's alpha 0 plus beta 1. What
Yeah.
are you gonna do with it? Measure it? I guess you have to measure it.
Yeah,
And then you get your bit, 0 or 1. I can send you 2 bits, but you have to let me add an entangled qubit between you and I. So now you say, oh, there are 2 qubits then actually. Yeah, but there's a theorem that says that the qubit that is entangled cannot be used to transmit information, so there's still something mysterious over there. And I include that in the thing, those 2 theorems make it look surprising that we can send with 1 qubit and an entanglement between the 2 of us, I can send you 2 bits. Because if I give you just 1 qubit, say with teleportation, you can only get 1 bit when you measure.
Mhm.
It's communication though.
But the problem, I mean, the problem is with the information that, because you don't know what you get when, even if it's entangled, you don't know if it's get white or black when it gets out. Right, that's.
If it's entanglement, you
I
will
mean,
have
you
instant,
look and you know that the other one sees the
Yeah.
white too.
but you don't know what you're gonna get.
But you don't know if you get white or black, so.
Correct.
How is it useful? I don't see, the moment I will see they.
Correct, that's the whole point, they have the density matrix is such that you can prove that with an entangled qubit, you can't send information, it doesn't have information that you can send. It, however, supports communication.
I don't see it yet. but I
Exactly,
will.
I understand.
I hope I will.
So hopefully, but people, you might say, there are 2 qubits, so why are you saying it's so incredible that you are sending 2 bits, because you have 2 qubits. The communication qubit and the entangled qubit, okay? So why do you say, the thing is that the entangled qubit can be used to send information, it's not carrying any information. So there is entanglement there, and then the qubit which you are used to send it to you, that is just 1 bit of information when you measure it. So it's still interesting.
So what is measuring? What is measuring?
Oh, you know what? I'll give you an answer. Measurement is entanglement with the apparatus.
Okay,
That's what they think it
and
is.
that's an instantaneous, like, one moment.
Well, at some point, that instantaneous thing is going to collapse to a classical value. So measurement simply says, you have a qubit, you want to measure it. With a certain probability, I'll give you either 0 or 1.
Yeah, so you're forcing that
Exactly.
wave function to collapse to a
Exactly.
value.
Yeah.
But is that a thing that you can only do at one moment, or can you like observe it
No, you cannot. observe it.
consistently?
No, you cannot, you don't know it, actually.
But you measure it like and force it to stay in that state for like
First
a
of all,
prolonged period of time?
keeping it in that state is a problem. Because it's almost like, well, that's the problem, it has to be a fast state. But interaction with the environment forces it to decohere. It just goes on its own to 0 or to 1. So they work in nanoseconds or because the qubit doesn't last. And they want the calculation to be faster than how long the qubit lasts. It's hard to keep that qubit there.
Oh, it'll eventually just,
Yeah, it's like a spring, you know?
yeah.
It has 2 states, I mean, not really 2 states, only 1 state. I guess it has the largest deformation state and the state where it doesn't do anything, okay? So you could put it any way you want, but when you leave it, it goes through some oscillations back to that state of equilibrium. So can you observe it with a spring? Yes, you can, but can you keep it there? You have to apply force.
So even like entangled qubits. Don't stay entangled. That's a short
Yeah,
relationship
yeah.
and the, okay. Hmm,
So you hear about quantum memories. Well, that means that I can hold on to those things for a long time.
But have they not said that they have measured entanglement from in the space somewhere to the bird or something? It's a really big distance, so somehow it has to stay a long time alive, but they can do that.
So maybe like you can trap an ion, you could also say, I know what state it is and I wanna hold on to it. Then I have to apply some control, where if I think that it's too long, since too long, in very small interval of time. Then I actually try to set it more, and I just set it, and I set it, and I set it, and I set it. And I don't know where it is, but by setting it periodically, then maybe I can hold on, keep it in that state.
cause I was just thinking of like. If you could do that, obviously it wouldn't, I mean. If you could hold a entangled qubit in a state, that would effectively be communication with the other qubit, cause then it would be forcing that qubit to be locked. In that value.
Okay, so first of all, let me just end this. I'm gonna say stop recording. And say yes, and then I'm gonna